Let's do an angular acceleration problem. The propeller of a ship makes 300 revolutions while its speed increases from 200 to 500 revolutions per minute. So I know that this thing is going to be increasing its speed. It's changing it, so we have an angular acceleration here, and that's what they're asking us to find. So that's my question. And I get that it goes a distance, angular distance, of 300 revolutions. Its initial angular velocity is 200 revolutions per minute. Its final angular velocity is 500 revolutions per minute. And usually I get a time with this, but I don't get a time with this one. So I'm going to need some formula that helps me figure this out. So this is one that you need to have handy. Again, if you think back to your linear, final velocity squared is equal to initial velocity squared plus 2 times a times d. If I rearrange that for this, a equals vf squared minus v0 squared over 2d. And if I turn it into the angular version, the angular speed is the final angular velocity squared minus the initial angular velocity squared divided by 2 times theta. So now let's go ahead and let's plug it in and work it. So the final angular velocity was 500 squared minus the initial squared all over 2 times 300 revolutions. Okay, so don't make this mistake. Don't take 500 minus 200 and then square the result of that. You need to square these before you do your subtraction. Otherwise, you will get the incorrect answer. So 500 squared minus 200 squared is going to give me a really big number there, 210,000. The units are going to be revolution squared per minute squared all over 300, 2 times 300, 600 revolutions. Okay, let's do the units first. A revolution cancels, one of these revolutions cancel, and I get revolutions per minute squared, which is good because that is an angular acceleration. And then 210,000 divided by 600 gives me 350 revolutions per minute squared, and it's positive, and that's good because I know that I'm speeding up. All right, part 2 of this problem was, how much time did the increase in speed require? So, part B, what's the time here? This one's not too bad because I know that time is final velocity minus initial velocity divided by acceleration. In this case, it's angular, so the time is equal to the final angular velocity minus the initial angular velocity all over the angular acceleration. Let's go ahead and plug that in. Final is 500 revolutions per minute minus 200 revolutions per minute divided by 350 revolutions per minute squared. Okay, so we're going to have 100 minus 200 equals, divided by 350, and I get 0.86. And then if I got revolutions per minute divided by revolutions per minute squared, I know this is supposed to be a time. It's going to end up in minutes. And if you want to see that, let's just look at it quick. Revolutions per minute divided by revolutions per minute squared would be like multiplying by the reciprocal, minutes squared over revolutions. And sure enough, revolutions cancel. this minute cancels, one of these minutes cancel, and I'm left with minutes. So that's a double check on our units, and we did the right thing. So again, the angular acceleration was 350 revolutions per minute squared, and the time it takes to do that was 0.86 minutes.